continuing. There we go. And did I start a browser? Nope. So the browser is here. And let's get back to the slide that we were on. Did anyone try to finish the trace of the A-star algorithm? Okay, sort of, okay. It really helps if you just give it a little bit of attempt, because even if you did not finish it completely, just the attempt to do it would make you understand the algorithm a little bit better. So in class you'll be able to follow the trace a little bit better too. All right, so getting back to graphs. So we're going to go back and talk about the terms a little bit later, but I want to finish the A-star algorithm first. So that's why we're working on this one first. Actually, I think we did not do it this way. We did it with the practice exam first. Okay, so let's do that first. And the first thing I can do, I forgot to do this first, is to share the exam with all of you, because I think last time I forgot to do that. So this exam is 2016 fall, and let me copy this to the folder where you guys can see. So we'll make a copy to the folder that you can see, which is the shared folder. And of course I can't see, I can't see where I can click a button. There we go. Click OK. All right. So I think you should be able to see it now. I'm just going to double check, make sure that I can see it in the shared folder first. It's a F16 fall 16 final exam. Copy of, oh, there we go, excellent. So it is there. You can actually refer to the algorithm on your mobile device if you want to. So I'm gonna open it here and display the algorithm itself. Are there any questions from last time? Are there any questions about the algorithm itself from Tuesday, from our Tuesday discussion? No questions about that? The notations are okay? Because that's one of the bigger problems is if the notation itself is not understood, there's no way you can actually stimulate the execution of the program. Okay, so if there are no questions about this, then I'll go ahead and open up Mousepad. And this time I made sure that I saved the file, so it should still be here. All right, cool. So we can continue the trace. So this is the current state of the algorithm. We are done with the second iteration of the while loop. We picked out vertex C to explore, and then we looked at all the neighbors of vertex C. So let's check whether we have already explored all of the neighbors of vertex C. So one thing we have to do is to go back and look at the graph itself. We look at vertex C, it has two neighbors. We have only explored one. So the other neighbor we have not explored yet, so it's time to do that. If I remember correctly, I put this tab over here. So this way we can look at the graph at the same time when we perform the logic of this code. So the one neighbor that we did look at was vertex D. So we have to look at the other neighbor. So can someone just look at this algorithm, look at the graph, and tell me which other vertex should I look at?
B.
Vertex B, very good. Okay, so let's go ahead and do that. So continuing from the previous trace, this is iteration 2 of the for each loop. Okay, and inside here, the first thing we do is to initialize variable n, which is the neighbor of vertex C. This time we'll pick the other one, which is vertex B, and then we'll compute t. Okay, so do you remember what t stands for? Yeah, what is the variable t doing in this algorithm? What is it representing? Okay, let me scroll down a little bit. Okay. So here's t. T is always g of c, which is the node that is that we are looking at, plus the cost of an edge. In the previous case, the edge is CD. So what do you think t itself is representing? In other words, what is the meaning of this particular sum?
From start to
This is the cost of a path, right? Not necessarily the cheapest, but it is the cost of one path from the start state S, which in this case is A, to the destination state, the destination vertex, which is E in this case. Yep.
Is there more code a little bit higher up on there? I just remember from last class that we weren't looking at this part of the code when we were discussing
We weren't looking at.
maybe there were lines higher where there was like an if, there was a different if statement.
We did look at this.
Remember you asked us a question about like Xing the loop, like could it go on infinitely, and then you were analyzing another part, and I know like G
That was before we started the trace.
this is before that.
Yeah. So I think this is where we left off last time. Otherwise, I wouldn't be saving the file. Okay. So in this case, since we picked out B as the neighbor that we're exploring, so now it is g of c. We want to compute g of c, which is the cost of the shortest path known at this point. Okay, it may not be the actual shortest one, but it's the shortest that we have that we can confirm at this point, plus the edge from from C to B in this case. So we just add D, which is the distance of the edge. In this case, it's CB. So this particular sum is going to tell us the cost of a particular path going to B from A. Okay, is it going to be the shortest one or the least expensive? We don't know. Okay, we'll find out. Okay, so looking at the table, looking at the g's that we have already initialized, g of c currently has a value of 1, which means the shortest path that we know at this point, or the cost of the shortest path that we know at this point, has a cost of 1 going from A to C, which is kind of natural because that's the only edge connecting A to C. And then we're going to add the cost of the edge CB. So we are looking at the cost. So we know from A to C it will cost 1. We also know from C to B it's going to cost 2. So the sum of this is just 3. The next question, or the next thing we have to do, is to compare and say, is this number 3, is it less than the cost of the shortest path known at this point from A to B? Well, we know that is 4, okay? In other words, previously, because we started with A, which has a direct edge connecting to B, so previously the cost of the shortest path from A to B has 4 units, okay? It would cost us 4 units. But now that we have found a shorter path, we have to update it. So T in this case is 3, which is in fact smaller than G of B. So that means we have to go into the conditional statement and then do all these other things. So the first thing we have to do is to make sure that B is in the big O set. I chose the letter O for open, okay? So this is a set of vertices that are considered quote-unquote open, which means, we have to look at those again because we found a shorter path, okay? So that's why we have to make sure that B is in it. But B is already in it, so that's okay, that's cool. So E, D, B, it's still the same because, adding B to this set doesn't really do anything to it. We have to update the previous of B to be C, which is basically saying, hey, we just found a shorter path to go to B, and it is coming from C. Because previously it was coming from what? What is previous B? A, exactly. So we have to update it. Because in the end, what we want to do is to use the previous to track our way back to the start vertex from the end vertex. And that's why the previous is going to be helpful at that time. Okay, now we just have to update g of b, to be the new number, which is 3. And we also have to update f of b. But what is f of b? What does it do? What is the purpose of the function f? You guys are not remembering. Okay, f of b is an estimate, okay? It's an estimate of the cost of the shortest path from the start state, or the start vertex A, through B, in this case, to the destination, which is E. Okay? So the way we compute this is just to say, oh, then it is just g of b, because that g of b tells us what is the shortest path, or what is the cost of the shortest path from the start vertex to this particular vertex b. But we have to add something. We have to we have to add the heuristic of going from b to e, because the heuristic is a rule of thumb. It's a very easy. Is a function that is easy to compute, but it is always an underestimate of the actual distance. So in this case, since I gave you the definition of HBE is 1, so that's just adding 1. So 3 plus 1 is 4. And that's the last thing we have to do inside the conditional statement. So as a result of what we are doing here, let's go ahead and copy and paste this portion, because this makes it easier for us to visualize and look at both the graph and also the numbers at the same time. So this time we have to update g of b to 3, f of b to 4, and previous of b to be c. Are we still doing okay so far with this? Okay, all right. Now that we have explored both neighbors of c only has 2 neighbors, it's time to get out of the for each loop. But since the for each loop is also the last thing inside the while loop, we're going back to the beginning of the while loop. So let's check out the while loop, okay? Because you may not remember what the while loop looks like. This is the while loop. So the while loop says as long as the open set big O is not empty, we'll have to continue with the next iteration. It is not empty, so we have to continue. So we have to pick the next vertex to explore, but we are not going to randomly choose one, because we want to choose the one with the least f value, okay? So let's switch back to the graph itself, switch back to here. So now we have to look at what is in the set O. We have E, D, and B in big O. Which one has the least f value? So we are looking at B, D, and E. Which one has the smallest value? B, okay, so that means B is the most promising candidate at this point. Okay, remember the f value is basically saying, okay, this is the estimate of going from the start vertex through vertex B to the destination, and it is the least expensive amongst all the alternatives. So we are choosing the most promising candidate to explore. It's like, okay, let's pick this one and explore it first. Okay, so that's good, because now we know what our variable C would look like, because variable C in the algorithm is just going to be vertex B, and the set O now has to be updated because B is now chosen, so we don't want it to be in the set anymore, so we are removing B from the set O. And now that we know this part, it is time to go into the for each loop. So we say iteration, okay, make sure it's indented a little bit, iteration 1 of the for each loop. The for each loop inside the while loop is to explore and look at all the neighbors, in this case of vertex B. Okay, so we look at vertex B only has one single neighbor, which is E, so we'll take a look at that. So variable N is going to be, in this case, the only neighbor, which is E, and it is time to compute our variable T. So once again, variable T is an estimate of, okay, so if we go through vertex B, in this case, to vertex E, what is, the cost of that? So it is G of B, which is the cost of the shortest path to B at this point, plus the distance of the edge BE in this case. So G of B we already know is 3, and the edge itself has a cost of 1. 3 plus 1 is 4. Okay. So now the next question, or the next thing we have to do is to say, have we found a shorter path to get to E in this case? Now, E being the destination vertex has no special meaning in this particular case. Okay, so we are not, considering E to be special because it is our destination. We are doing the same logic, just as we did with all of the other vertices. So we are looking at T and say, is it less than the shortest path that we already know at this point? That's the question. And the answer is yes, because the shortest path known at this point has a cost of 25. 4 is definitely less than 25, so we go into the conditional statement and perform all of these operations. So we look at big O and say, we probably need to put E into big O, because we are just going to update the shortest path, or the cost of the shortest path to E. So big O is now going to be ED, just like before, because it was already on that list, on that set, in that particular set. So that's cool. The previous of E is no longer what it was before, because previous E was A. It is now going to be B. G of E is going to be updated to T, which is 4. And then the last one is also going to be 4. F of E is also going to be 4, because the heuristic of going from E to E itself is 0. Are we still doing okay so far with these updates, and why we have to perform these updates? Okay. All right. So just like before, I'm going to copy and paste all of this stuff here and reflect the changes that we have done. So G of E is now 4, F of E is also 4, and previous of E is now B. Is that okay? Are we done? Well, when you look at the while loop, we're not done yet, okay? Because the while loop will only exit when big O is empty. Big O still has 2 elements left, so we're not quite done yet. I cannot remember which iteration is for the outermost loop.
We're in the 4th iteration.
It's 3. 4. So we got iteration 3 somewhere. Okay, this is iteration 2, choosing C. So we should be in iteration 3 of the while loop. So in iteration 3 of the while loop, we have 2 elements in the set O, which are E and D. And amongst these 2, we have to choose one based on their F values. We want to choose the one with the least F value. D has an F value of 10, E has a F value of 4, so we're going to choose E because it is the most promising candidate at this point. Okay, so we say var C is E. Then we have to remove that from the big O set itself. So big O is now just with D remaining. And then we have to look at it for each iterations. So this is iteration 1 of the for each. Okay. Well, do we have to do anything here? Does E have any neighbors? Does it go to any vertices? Nope, we're done. Okay, that's one easy iteration because we don't even have a single iteration here. Going back to the main loop, so now we're going for iteration 4 of the while loop, and this time we don't have a choice, okay, because we only have one element left, which is D in the set O. So that means we have to choose that one. So O will become an empty set at this point. So the next thing we have to do is to look at all the neighbors of D. D has one single neighbor, which is E. So we say iteration 1 of the for each loop, and var n, which is the neighbor, is easy to compute because D only has one single neighbor, which is E. So now we have to compute T, which is the cost of going through D to E. So now we have to look at G of D plus the distance of the edge DE. Okay, we can look it up here. G of D has a value of 8, and the edge DE has a cost of 3. So 8 plus 3 is 11, so t is 11. So now we have to ask the question, is t less than g of e? Have we found a path that is less expensive than the one that we do at this point? The least expensive path that we have known at this point? And the answer is no, because t is 11, g of e is already 4. So we have not found a shorter way to get to e, so there's nothing to do. We skip all the way to the end of the conditional statement because the condition itself is false. Okay? So now we get back to the while loop. We're done because the big O is now empty. It's an empty set. It failed to meet the stay in loop condition, so we are done. Are we okay so far with the trace of this algorithm? And can you see why the A star algorithm can find the shortest path? Okay. Any questions at all at this point about the A star algorithm? Can anyone look at this algorithm and understand why if h is not an underestimate of the actual shortest path, then we may actually miss the shortest path? What is h again? What are these numbers? They're heuristics, right? But what is the purpose of the heuristics?
Underestimated value.
Well, we want it to be an underestimated value, but what is the purpose? Why do we want to use heuristics?
To see the shortest path.
Because it gives us a way to sort of look ahead and eliminate obviously bad options.
Exactly. So it's kind of like a look ahead. Exactly. It's a very inexpensive way to compute look ahead value. Okay, because the actual value is the shortest path, right? But we don't want to spend all the time to look at to actually explore and find out what is the cost of the shortest path. So the h or the heuristics is a very easy to compute function, but it will give us an idea, okay, of whether we are looking at a good option or a bad option. Is that okay? So what if the h value or the heuristic value is actually greater than the cost of the shortest path? What would happen?
Probably would never check that path then because you're
But why would we not check out that path?
it'll make f bigger and then when you compare f's,
Yep.
that's not right.
Well, it will still be, if it is in the big O, it will still pick it out, right?
Because what if there was like a path that its length was the exact same size that had the heuristic that was covering up something smaller? You can skip over it.
It will skip over it because, okay, so let's take a look at the algorithm itself. Oh, interesting. That's cool. So if you look at the algorithm itself, the f value is only used when you already have that element, when you already have that vertex in the set. So that's the only time when the f value is actually utilized. Okay? So that means if you have a heuristic that is poorly constructed and it is not always an underestimate of the shortest path, it is only utilized, it's only used when it is prioritizing, which one to use or which one to explore first. So even if your heuristic is really bad, okay, it will still look at it just much later. Any idea why, if your heuristic is not an underestimate, we can potentially miss the shortest path. Okay, so let's just say that it is a bad one. We evaluate it last. Okay, because everything in big O will eventually be explored. We know that one because big O has to be empty in order for us to exit the loop. And then for each iteration of the for loop, we are going to remove exactly one element from big O. So that means even if it is not rated correctly, it will still be explored. But it will be explored later than what it should be. okay? So how is this going to affect the, it eventually has something to do with this as well, okay? Eventually it has to do with, no, I take it back, sorry. It has to do with this part here. Let's go ahead, okay, to answer that question, let's construct a case, okay? So that, we will basically make a heuristic function that is not an underestimate, and as a result, the shortest path is not found. Is that okay? So we want to trick the A-star algorithm by not meeting one of the assumptions, which is the H value has to be an underestimate. And then we want to see, oh, okay, so in that case, we are going to skip the shortest path. We are not finding the actual shortest path. Is that all right? Okay. All right. So let's go ahead and figure out how we can kind of hack this particular diagram to make it like that. The shortest path at this point, if you just visually take a look at this, you know the shortest path already, right? The shortest path is A, C, B, E. Oh, you know what? I forgot one thing. Forgot one thing that is really important, because we did all this computation, but I forgot to tell you guys, how do you read the previous in order to find the shortest path? The shortest path is in here already, okay? If you look at all of these things, especially the previous, the shortest path is there already, except it is spelling backwards. Because what you do is you start with E, and you find out that, oh, the previous of E is B, and then you look up B and you say, oh, the previous of B is C, and then you look up C and the previous of C is A, which is our start vertex. That's how you reconstruct the shortest path after the A-star algorithm is completed. Is that okay? And that's also exactly why we have to keep track of previous, because otherwise you can find the cost of the shortest path, but you won't know exactly what edges you have to go through in the shortest path. Is that making any sense? Okay? All right, so I forgot about that part. Now that we know that the shortest path is this, okay, we want to hack the heuristics so that we would terminate the loop, the while loop, prematurely without exploring everything here. So which heuristic do you think we have to mess with in order to miss the actual shortest path? And how do we update these things so that the shortest path will be missed entirely? I want to do the minimum edits, okay? I want to do the minimum changes in order to kind of trick this algorithm into that problem. Okay, so let me make a copy of this thing first, okay, so we don't lose the original. So copy, and I'll scroll all the way to the end. Well, maybe not that. I will put it before, right here. There we go. I don't want to put it all the way to the end because that would take a lot of scrolling to go back and forth. So I'll just put it over here and double click so I can edit it. All right, so we want to hack this a little bit so that it doesn't work anymore. Okay, so let's see. We can move this over here and make the text just a little bit wider. There we go. Okay. We know the shortest path is this one. We don't want to change that. We just want to mess around with the heuristics so that that is no longer going to be found. Okay? Now you might think that we can just mess around with the heuristic of BE. That will not change anything, because remember, by the time we have B in big O, it is bound to be explored. So changing BE, the heuristic of BE, is not going to be able to effectively change the algorithm so that it would totally miss the shortest path. Okay? We can change that, it's just not going to be very effective. What else do you think would be good to change? Now BE can be changed, okay, so let's change it to 100, which is like way more than the cost of any other path, so we'll change that. Which other one do you think we have to change? So that we don't even get to B. Change C, yep. So we'll go ahead and change C and say this is 100 as well. Okay. The rest, we don't have to change, okay? We'll just leave the rest the same. So let's go ahead and just go through this mentally and see if we can figure out, oh, okay, so that is effectively messing up the algorithm. We're not going to be able to track, those things anymore. So this time, what I'll do is I'm going to save this first so that you have that in the main document as well. And instead of tracing the algorithm, going back and forth and using the conventional method that we used last time for tracing, we'll do it in a shorthand way. Okay. So initially, O has one single element, which is the start vertex. This is how we initialize O before entering the while loop. Okay. We also know how we initialize all of the other values, don't we? Because we know all the G's are supposed to be. Do you remember how we initialize everything? Before you even look into the graph, what is the assumption of the cost of the shortest path to a particular vertex? Infinity. Okay, we just say that maybe it's not even reachable. Maybe there are no edges connecting to those particular vertices, except for A itself, right? Because the cost of the shortest path from A to A is 0 because A is there already. So that one is this is how we initialize G of A. But G of B is going to be infinity. G of C is infinity. G of D is infinity. G of E is infinity. What about the F values? Okay, the F values are basically looking at the heuristics and go like, okay, what is the estimated cost of the shortest path from the start state going through this particular vertex to the destination vertex? That's what we're asking. So in the case of A, it will just be the heuristic of AE. So the heuristic of AE has not been modified, it is still 3. All of these other ones are going to be infinite. So G of B is infinity, F of C is infinity, F of D is infinity, F of E is infinity as well. How did we initialize all the previous? The previous of A is the only one, well, they're all unknown. Okay, they're all initialized to unknown because without actually exploring anything in the map, you don't even know whether things are reachable or not, whether there's an edge connecting to it or not. So you can only say that they're unknown. Okay, we don't know whether there's a previous to those particular vertices. So E, that's unknown as well. Okay, so that's how we initialized everything. In the first iteration of the loop, we don't really have a choice of which vertex to explore. It has got to be A. So var C is going to be A, which means O will now become an empty set. Then we get into the for each. We look at all the neighbors of A, right? So there are 4 neighbors of A, and for each neighbor, we're going to have to compute T. So for neighbor being B, we will compute T to be G of A plus the edge of BE. Oops, sorry, AB. G of A is 0. The edge AB has a cost of 4, so this is going to be 4. T is less than the current G of B, so we're going to update these numbers. So we'll go ahead and update all of these as a result of that comparison. So G of B is going to be updated to 4, which is what we see here. F of B is kind of the important one, because F of B is going to be G of B, which is 4, and then plus the heuristic value going from B to E. That's how we changed things from last time. So this time, so B is going to be, I don't think this is going to work out because B is in the set O, and as long as B is in the set O, we'll still find the shortest path. Not sure whether you guys know do you know what I'm talking about? So we have to do one more edit to the graph in order to illustrate this example. We have to remove that edge going from A to B because we cannot have B in big O to begin with. Is that okay? Okay. So this has to go. And I'm just running this algorithm mentally to make sure that, okay, by the time we explore C, C will still put B onto the into the big O set, so it's not going to work out either. Okay. So we have to make it so that it doesn't put B into the open set. In other words, the graph that I have at this point may be too simple to illustrate what I want to illustrate. So I'm just going to I'm going through all the mental math to see if there's a way to make it work. So A is the start state. It has to be in the open set. And then the neighbors of A will also be in the open set. So C is going to be in the open set. So the rationale is, how can we not put B onto the open set when C is in the open set? So we have to have a way to go to. There's no way that is going to happen because B is initialized with an infinity as G of B. So that's always going to be less. So I think we need one more vertex to make this work. Okay, so let's go ahead and make one more vertex. The Control D, we copy this. Okay. Of course, this cannot be B anymore, it has to be something else. And then we need one more edge to go from here to here, because if it's linear, it will still do all the exploration. Unless the cost is already too high. Let me think about this a little bit. Okay. This is 25. This is 1, this is 7, this is 3. And I still want this to be the actual shortest path. Which means the total cost has to be less than 11. Make this 9 and make this 1. We'll change the name of this node here to F. There we go. Alright, so from A to C it is going to be 1, and then from C to B.
That's 12. I think that's.
Sorry?
I think it's 12. It's not the shortest path anymore.
The shortest path is
C to D to A, E.
It is the same length.
AC is, yeah, it's same length at this point.
Okay.
So we have to tweak some of these. The idea is not to expand one of these particular cells. And in order for a particular, not cell, but one of these vertices, we don't want to put it back in, put it into the big O. So in order to not to put it into the big O, the set of big O, let's look at the algorithm. So in order to get it, not to put it into the big O, we need this condition to be false. In other words, we would think that we already have found a shorter path, and the new one is not going to be smaller than the one that is already found, so that it will stop and not put it into the big O set. Because once it's put into the big O set, it's not gonna work anymore. Okay, so So we'll need h of fe has to be something, it is to be determined. Okay. So C is going to be in the open set for sure. D is going to be in the open set for sure. But when D is in the open set, it will explore B. And the idea is by the time it explores B, we don't want it to put B back into the open set and just say that, okay, this is it's already. But in order for B to have a value, it has to be in the open set initially. So we need an edge going from A to B. I'll think about this, and finish the example because I don't want to use class time to do this. I just thought of, this would be a good exercise to kind of illustrate an example where the heuristics will trick the algorithm so they cannot find the shortest path. So it was kind of unplanned for. Okay, so I'm going to work on this one a little bit and make it a homework assignment. I think it would be a good homework assignment because you will have a chance to actually go through this manually and be able to understand the algorithm a little bit more, and also in this case understand why the heuristics can mess up the property of the A-star algorithm. Okay, so having the heuristics not being an underestimate will have a side effect of not finding the shortest path. I just have to find an example to make it happen. What if I turn all the heuristics to zeros? What would that do? In other words, from any vertex, I say, oh, the estimated distance from here to the destination is 0. In other words, the heuristic is not informing me of anything anymore. It's not helping me in any way.
You'd have to randomly just check everything.
It won't have to check everything. It will still be able to terminate without checking everything. It becomes breadth first search. Now, since all of you are supposed to be taking cisp440 at the same time, have you guys talked about the breadth first search approach in that class? Yes? Okay, no, I hear some heads turning and some heads nodding. So, okay, can someone tell me what is breadth first search as opposed to depth first search?
The size of the trees. How wide the tree is.
Okay, so in the tree representation, okay, so I'll just take a look at this tree here with 7 nodes. We'll call these A, B, C, D, E, F, G. And this is how the tree is connected. Okay, it's a binary tree, just like that. It's not a binary search tree, just a binary tree like that. There are 3 ways of traversing a tree. Can someone tell me the 3 ways of traversing a tree? Pre-order, post-order, and then in order. Okay, but those are all depth first. Okay, they're all based on the depth first approach. So the breadth first approach, breadth first search or traversal, is going to explore this first starting with A, which is the root, and then BC. Now the ordering amongst BC we don't know for sure because it is, we don't really indicate the ordering between BC. And then it will explore the last tier, which would be D, E, F, G. Now the ordering among these 4 we don't know for sure either because it's just whatever is at the outermost edge of this from this root. Is that okay? So that's breadth first search. If you make the heuristics 0, it will basically transform the A-star algorithm into a breadth first search approach. Does it make any sense? Okay. When you look at the definition of the functions, what would having all the h values being to 0, what would that do to our functions? In other words, what would that do to? Would it impact g of v at all? No, but would it change f of v? How is it going to change f of v? you look at the algorithm and you look at how we update f of v. That's the only place the heuristics is actually used. F of v is 0 plus hsx in this case. F of v is gn plus hnx. So those are the only two cases in the entire algorithm where the heuristics is actually utilized. And in both cases, they are utilized to compute the f value. So when you have all the h values being 0, what is that going to do to f? F becomes the same as g, okay? In other words, the cost of the known shortest path to a particular vertex is going to be used to prioritize, oh, who should I be looking at next? Who should I be exploring next, right? So what would that do to your search algorithm?
You need to pick out of order.
Sorry?
You need to pick out of order. You need to go on.
It would still keep the same mentality of I would choose the most promising one, but it has no future outlook anymore. In other words, it's all based on the cost of the known shortest path to a particular vertex. And that basically turns the A-star algorithm into the Dijkstra algorithm. Okay? So that's why I don't use the Dijkstra algorithm, because it's quote unquote a special case of the A-star algorithm. Okay. Is that okay so far? Okay. So now would be a good time to kind of go back to the notes, and we'll go ahead and go back to a previous slide to talk about the terminology. Okay, because I skipped that part to work on the algorithm first, but now that the algorithm itself is discussed, we'll go back to some of the terms. So graph theory, which is the first link, is the one that talks about all the terminology. We have already talked about how a graph is represented by a two-tuple. One set is the set of all the vertices, and the other one is the set of all the edges. So we talked about all of this stuff already. So we will go ahead and just talk about the terms in graph theory. There's no proof whatsoever here. They're only the definition of terms. The first one is, what is the word order? What does it mean in graph theory? The word order is really just the cardinality of V. In other words, how many vertices do we have? That's the order of a graph. So the one that we have been working with has an order of 5 because there are 5 vertices in that particular graph. There's another term to refer to the number of edges. It is called the size of a graph. So the size of a graph is the cardinality of the set of all the edges, which is basically just saying, okay, how many edges do we have in a graph? Is that okay? Is there a particular relationship between V and E? The cardinality of V versus the cardinality of E. Without looking at a particular graph, can anyone establish a particular relationship between those two? Does one have to be greater than the other one?
V has to be greater than or equal to E. I mean, less than or equal to E.
Nope, does not have to be the case. So let's just say that we have a graph of 3 vertices. Okay, so we have vertex A, vertex B, and vertex C. This can be the entire graph with no edges. Okay? So there's no guarantee of the cardinality between V and E. Now, if you really want to put an upper bound, you can put an upper bound. Okay? So the cardinality of E, cannot be greater than, or E cannot be greater than a particular number. And if we assume that you cannot have a vertex with an edge going back to itself, okay, and this is directed, which means all the edges are arrows, and they're distinct. Okay, so the edge from A to B is distinct from the edge from B to A. Okay, so what do you think? This cardinality. What is the upper bound of the cardinality of E? Okay, so you use examples. One single vertex. With a single vertex, can we have edges? I already said that you cannot have a vertex. You cannot have an edge going from a vertex to itself. So with a single vertex, you cannot have any edges. Okay? What about with two vertices? How many edges can we have? That can be we can have a we can have an edge going from A to B, and since this is a directed graph, we can also have an edge going from B back to A. But that's it, right? What about three? A, B, C. The vertex from A to B, another one going backwards. B to C, C back to A, C back to B, A to C, C back to A. That's it. Okay? So when you look at this, what is the pattern here? Oh,
Is it cardinality of V factorial?
no.
Just 2n.
It is not factorial. It has to do with square. But the question is, what thing to the power of 2? That is the question.
N to the power 2.
Okay, so if we know it's something like that, okay, so what goes inside the parentheses? It's not V, it's not the cardinality of V, because otherwise, with one single vertex, we will have one single edge, right?
The cardinality of V minus 1.
Yep, that's it. Which makes sense because every vertex has a, let's see, would that be the case? Nope. I take it back. I messed up. There we go. It's not a square because for each vertex, it has the cardinality of V minus 1, which is itself edges going out. So that is, this bound has to be there. When we have those rules of you cannot have a vertex, cannot have an edge going to a vertex itself, and it's a directed graph, then this is the upper bound of the number of edges. But the number of edges can be anything less than this particular number, less than or equal to that number. Is that okay so far? Okay. So we call a graph being simple if and only if this thing is true. So, okay, so let's read the English part first. In other words, there's up to one edge between any two vertices. Okay. So then we take a look at this statement and try to find out what it is. Okay, so let's start with this part here. What is that saying? For all V and W being elements of V. Now V can be the same thing as W, like we're just saying, okay, let's pick any vertex, as V, pick any vertex as W. The following has to be true. So what is the following that has to be true? Okay, so we look at this part here. That is interesting. If I click it, it moves a little bit. Okay, so we are looking at the cardinality of something. The cardinality has to be less than or equal to 1. The cardinality of some set has to be less than or equal to 1, so now we have to take a look at, okay, what kind of set are we talking about? This is a set of edges, okay? Because the first thing we see is, okay, for every element in this particular set is E, but E has to fit the following description. E has to be an element of E first, uppercase E, which means it has to be an edge. Okay, this part is saying E has to be an edge. And then this part is saying E equals to VW or E equals to WV, which means E is either going from W to V or going from V to W. So if a graph meets this requirement, between any two vertices, there's only up to one single edge, then the graph is known to be a simple graph. It's just a terminology. Would this be a simple graph? I'm just pointing to the ABC with all the possible edges. It's not simple anymore because between B and C, we have two edges. Okay. What about the tree? Well, first of all, is a tree a graph? The tree has nodes and leaves. Those are your vertices. And the connection of the nodes to nodes or node to leaf are edges. So every single tree is automatically a graph. So if you want to find the shortest path between any two nodes in the tree, you can apply the A star algorithm. That will work. A graph that is not simple is called a multi-graph, so that's just a negation of this condition. The complement of a graph is, in terms of notation, if the original graph is G, which has VE as the vertices and the edges, and then we define the complement with a G and a bar on top of that, it would have the same vertices, but the edges will be the complement of the other one. In other words, when you have a union of E prime and E, you will have all the possible edges. Which also means, for all VW in V, if VW is not an element in E, then it will be an element of E prime. E prime has all the quote-unquote missing edges. Is that part okay? Okay. Two vertices VW are called adjacent in the graph if and only if an edge VW does exist in E. And also the opposite is also in E. So VW are called adjacent when you can go from V to W, but you can also go from W back to V. Then they're called adjacent. In the graph, G equals to VE, VW as an element of E, that's an edge, VW is an edge. V is known to be a tail and W is known as a head. Now that is not intuitive, depending on how you look at it. Okay, so it's basically saying if you have a vertex A and a vertex B, and you can go from A to B, which one is the head and which one is the tail? The one that is starting is known as the tail, and the destination is known as the head. This is not intuitive, especially if you are taking 430 with linked lists, right? But it makes sense when you look at this as an arrow, because the head of an arrow is the tip of the arrow, and then the tail of the arrow is where the feather is. Okay, so just remember, this is a weird definition of what is the tail and what is the head. Because typically when we think about what is a head and what is a tail, the head is where we originate from and the tail is where we are going. But in this case, it is opposite because we are looking at it as an arrow. So just remember, the head and tail refer to the head of an arrow and the tail of an arrow. All right. In the graph G equals to VE, the in degree of a vertex E is blah, 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 blah. So if you look at this thing here, what is it really saying? Okay, we're interested in vertex V. We want to know what is the in degree of a particular vertex E. So when you look at the cardinality of this particular set, what is in this particular set? So the first thing is not even to count the cardinality, but to understand what is in this particular set. So we have to read the description and say that each element E in this particular set has to satisfy the following requirements. The first requirement is E has to be an edge because it is in uppercase E, which is the set of all the edges. So that's cool, that's an easy requirement. What is the second one saying? What is that saying? There has to exist a W, which is also a vertex, where the edge E is WV. What is that saying? W is the tail of the edge, and then V is the head of the edge. So how do we draw that WV in this case? So we have vertex W, we have a vertex V, because W is V. How do we draw the arrow? In which direction? W is our tail, V is our head. So you draw the arrow like this. That helps because now you see that this is an actual arrow as opposed to a symbolic arrow. Is that making any sense? So the cardinality is basically looking at how many things are pointing to V. Okay, if you have 4 vertices pointing to V, then the in degree is 4 for this particular vertex. Is that okay? Yep.
Sort of like a smart pointer, isn't it? Counting the number of
References.
to
Yep.
itself.
In a way, yep. It's counting references to itself.
Yeah.
Correct. Yep.
Just talked about that last class in 310. I forget the number of it. C++ with Fox.
Is it 400?
Yeah, 400.
400? Oh, wow. So they start to talk about, tracking number of references in that class. So that's good. Okay. What about out degree? Well, you can see that the definition of out degree is almost exactly the same, except in the in degree, the edge is WV, and then in the case of out degree, it is VW, which basically means we're counting the number of things that V can reach. If I start from V, how many vertices can I reach directly using edges from V? That's the out degree. So in degree and out degree are basically just counting how many edges are coming into vertex V, how many edges are pointing out of vertex V, how many edges are pointing out. A graph is complete if you pick any V and W in V, as long as V and W are not the same, that edge does exist in that graph. So that will make it a complete graph, which is something that we have worked with already. Is that okay? So in a complete graph, the number of edges is going to be the cardinality of V minus 1, and then the whole thing times the cardinality of V. Okay? So here comes the terms that are a little bit more confusing. A walk versus a path versus a trail versus a tour. Okay, so those are the confusing ones. The other ones, not so confusing, but these can be a little bit more confusing. A walk W of a graph is an n tuple of vertices. And I'm borrowing the bracket notation from arrays so that we can designate which one in the tuple we are talking about. So if we use the W bracket I close bracket to denote the ith item, which is 0 oriented, of the n tuple, and bar W bar, I'm borrowing once again the cardinality symbol, but this time it is applied to an n tuple, so it tells me how many things are in the n tuple, is the length of W. Then this is, W is a walk if this condition is met. Okay, so let's take a look at this condition here. First one is, how do we what is the boundary of I? Where can it start, where can it end? So when you look at this one, it says, I has to be inside a particular set. But what is in that set? What is the first thing you notice, that has to be true for elements in this particular set? X has to be a natural number. So that rules out all the negative values, right? Because all natural numbers start with 0, okay? And then the second condition is X has to be less than bar W bar minus 1. Now the reason why it's bar W bar minus 1 instead of just bar W bar is because we're trying to establish the next one too, so that's why it has to be 1 short of the index of the last item in the n tuple. Okay, so this part is really just binding, what values I can have. This is the part that really tells you about what is the requirement. What do these vertices have to meet? What requirement do they have to meet in order for W itself to be considered a walk? Well, for any adjacent items inside the n tuple, an edge must exist in the graph. That's all it's saying. So a walk is really just a whole bunch of vertices where you have an edge between every single pair of vertices inside the n tuple. Is that okay? Sort of? Okay. What about the path then? Okay, a path is a walk. Okay, so the first requirement of a path is Everything has to be connected by edges. All the adjacent vertices have to be connected by edges. But there's one extra requirement. You cannot have repetitions. Now in this case, a repetition is a repetition of a vertex. Okay? So you cannot have any repetition of vertices. It's a path, but without repetition of vertices. That's easy to say in English, but how do we say that in a mathematical way to define it? Why do we want to do something like that? I mean, if the English version is already clear enough that a path is a walk with no vertex repetition, why do we even care about the other way to express exactly the same thing, but in a much more convoluted symbolic way, in using only these symbols? Why is that important? You can use it to prove stuff, okay, but who's going to do the proof? If a person is going to do the proof, the person can easily read, oh, it's a path with no vertex repetition. It's a walk with no vertex repetition. So that's easier, okay? So why do we want to be able to express these things using these really kind of obscure, symbolic, way of doing things? Yep.
Is it easier to put into code so we can actually use it in the program?
Exactly. It is easier for a computer to understand these terms. Because the for all term, okay, the for all symbol has a very specific meaning. Element of has a very specific meaning. Equal to has a specific meaning. Implication has a very specific meaning. In other words, it is easier for me, it would not be too hard for a computer to parse what is highlighted on screen at this point and understand, quote unquote, understand what it means exactly. It is much more difficult for Google or Siri to look at this and understand what it really means exactly. You can try it now. If you have an iPhone, just ask Siri, what is a path? Okay. Okay, but then why do we want a computer to understand what is a path? Why is that important by itself? So we're pushing the reasoning one step further, because the first one was, okay, we want to use the symbolic or mathematical definition because we want the computer to be able to understand it. But why do we want a computer to understand it? I mean, you guys are not computers, and you guys are going to take the test, and you have to answer questions related to this. So why do we want to make sure the computers can also understand this? Yep. So it can do formal verification. Okay, that's exactly what it is. Okay, so we are kind of rigid when it comes to how to express these things, or at least we want to be able to use these symbolic ways to express the meaning of, in this case, a path. All right, so let's check out this definition and see what it means. So the first part here is also putting just a boundary on I. And this time, it's not much different from the one before, except it doesn't terminate with this -1 here. In other words, this I has to be a valid index into the n tuple, which is P. Okay, so that's the easy part. The difficult part, or the more difficult part, is this part here. So if I pick any I that is a valid index, what is the rest of this part saying? Well, let's check it out. Okay, check it out step by step. So for each I that I pick, then we have to look at all the possible j, which is also using this requirement. Okay, and you can see that I and j are coming from exactly the same set. Okay, so I and j are both valid indexes. And what is this part saying? I does not equal to j implies p bracket I does not equal to p bracket j. What is that really saying? Different items along the same walk cannot be the same vertex. That's what it's saying. Now, what if I and j are the same? If I and j are the same, what happens to this implication? It becomes true. Why does it become true? If I and j are the same, why is this implication becoming true just like that? Because in the implication, what is an implication? A implies B can be expressed as, okay, A implies B can be rewritten as not A or B, right? So that means if A is false, then the entire thing is going to be true. Because if A is false, the negation of A is true. But if one side of a disjunction is true, I don't even need to know what B is, right? So you apply that reasoning to what is highlighted in the projector at this point. If I equals to J, I does not equal to J becomes false. But that's the first part of the implication, and it is false, which means the entire implication is going to be true. So the only part that is important here is when they are not the same. Then we want to make sure that they are not the same vertex. Okay. All right. What about a trail? A trail is a walk, but this time we are not repeating edges. Can we repeat a vertex in a trail? What do you think? Yes, we can. Okay, so you can repeat a vertex in a trail. You just cannot repeat the same edge. So if you think about it as driving, okay, if you think about this as driving, a path is basically you cannot revisit the same point. Okay, you cannot be in the same intersection. You cannot see the same. You cannot be next to the same building, and so on. A trail means you can go through the same intersection several times. Okay, so the first path is going like this. And you go like this, you go like this, and they go through the same intersection. So if we look at intersections as vertices, then this graph is okay as a trail because we are not repeating an edge. Now, sure, we are repeating one single vertex, which is representing an intersection, but we are not going through the same section of the street twice. So that is okay. It is still, this is still a trail because we are not repeating an edge, even though we are repeating a vertex. All right. So now we have a tour. A tour is a trail where the first and the last vertices are the same. So in order to turn this graph into a tour, I can do something like this. That was a tour. Is that okay? And then the very last one is defining what is planar. A planar graph is one that can be drawn in 2 dimensions without any crossing lines. Now that is kind of interesting. So we want to see, when you're dealing with graphs like this, okay, how many vertices can we have in a graph and it will still be planar? And we want to have a completely connected graph. Okay, we are looking at completely connected graphs, and we want to find out, okay, when can we not put everything onto the same plane? One single vertex. Well, that's easy because we don't even have edges when you have a single vertex. It is planar for sure. 2 vertices. Now, I'm not going to draw the 2 edges because you can kind of collapse the 2 edges into one single one when we're just analyzing is it planar or not. Okay. Is it planar? Yep. 3 vertices. Is that planar? 4 edges, or 4 vertices. Now this one is a little bit tricky because you got these 4, okay, easy peasy. You got these 2. What about the other 2? It is still planar. You look at 5. Okay. 1, 2, 3, 4, 5, all the neighbors, easy peasy. Okay, that's easy. And that one is pretty easy too. And this one is easy. Oops. What about between these 2? There's no way to draw a completely connected graph with 5 vertices on a plane. Okay? But why do you think that is particularly important? Why do we have to define the term planar, in terms of graphs? Why is that important to us? I mean, after all, we live in a three-dimensional world, right? We're not living in a two-dimensional world, so why is that particularly important to computer science people, or to computers, or to people who actually design the circuit boards inside the computer, or to people who design the chips inside the silicon, how transistors are laid out on the chip? Why is that important? Yes?
Because you get more and more efficient routing for circuits. Like that more sense.
Well, because you want to find out, whether you can route the signals between components on the circuit board without, you want to see how far you can push it, right? Okay? Why do we want to push that? How many layers do you think a circuit board have on a typical motherboard these days?
Just one layer.
One layer? Well, if it's one layer, you can, even an Arduino has more than one layer. So let's check it out. I know we're running out of time, but this is important because I want you guys to understand why this is important. Why do we give this a particular term? Why is it, whether it's planar or not, why is that important? So we'll go to Newegg. I know you guys know many other places where you can find motherboards. I'm just trying to find out, how many layers your motherboards have. So we'll go ahead and look at components, we'll look at motherboards, look at, just any motherboards, okay? I'm not sure whether it's a part of the specification or not, but we'll find out. View details. And in specifications, let me look for the term layers. Nope, doesn't say anything about that. Okay, motherboard number of layers. Pretty sure that's a question that people have asked that. And with this type of thing, you have to look at the date too, because modern circuit boards have a lot more layers. So to this end, most motherboards have 8 to 10 layers for conventional designs, which means your super duper gamer motherboard may have even more because you have more components and they have more parallel connections. What does that mean when it has 8 to 10 layers? What does that mean? What is a single layer?
One sheet of copper.
Yeah, one layer is one layer of copper. Okay, very good. So 10 layers means you have 10 layers of copper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And between the copper is FR4. Typically it is called FR4, which is a fiberglass material. So you have fiberglass material like this. And the router, which is a particular software, a particular program that will help determine how to get a signal from one particular pin to another pin of another component or the same component. The automatic router will try to utilize these layers for routing purposes. In other words, routing means you have a logical connection between two pins of components, and then the router is trying to figure out how do I draw a copper line with these layers in order to make that connection. Okay? So when you encounter problems like this, okay, if you can go to a different layer, if you have a 2-layer board, then you can solve the problem because you can. So let's say the red line is on the top side, okay, and the blue line is on the back side. We can do it now, right? So the more layers you have, then you can do more difficult routing problems. Okay. What about manufacturing? From the manufacturing perspective, what do you think is going to happen with a 10-layer board? What is going to happen between the layers? They have vias, okay? So between the layers, they got the concept called vias. So a via can be between any 2 layers, like that, okay? What a via is first of all, is a hole, okay? So the hole has to be drilled at exactly the same coordinate on the layers that are affected. Okay? And then what they do is they put a little copper tube into here. They solder the top and the bottom. So now you have an electrical signal that can go from here all the way down to here. Okay? So a 10-layer board has all kinds of vias, internal. You cannot even see that because it is under the top and also above the bottom layer. And then all of these holes have to be drilled with high precision because they have to line up. Is that making any sense? And if you, in case you have a trace that is not manufactured or etched correctly and is shorting out something, but it's inside these layers, how do you find that? Well, it can be found, by testing the circuit board. So the quality control, of these circuit boards have, special testers to make sure that there are no shorts, unexpected inside these particular layers. A 10-layer board is not cheap because it needs all of these different layers, and each layer has its own copper pattern. So when you're looking at a circuit board, that is a 10-layer board, you are looking at basically a sandwich, okay, with 10 slices of bread and 9 slices of coconut, cheese, and whatever. Okay, but they have to line up. The difficult part is they have to line up exactly. Is that making any sense so far? Your cell phone doesn't come close to 10 layers, by the way, because your cell phone doesn't have high pin count components. Your cell phone utilizes chips that are chipsets. So one single chip is not just your processor, but it also includes the flash, the RAM, and many other peripherals. So it doesn't need a lot of external pins to be interconnected. So your cell phone doesn't have a problem nearly as bad as the motherboard of your computer. How many pins are on the DIMM, D-I-M-M? 168. 268. Because if we are talking about DDR4 these days, yep. So if you think about the RAM module, each module that you plug into your motherboard has 200 plus pins. Where are those pins going? They go straight to the CPU because we don't have North Gate anymore. So they go straight to the CPU. How many pins do you think your CPU has these days?
1,000 to 2,000 processor. Server boards have more like 2,000-ish.
2,000 pins for one single chip. Okay? So how do you even get all those pins out from the inside the package? Okay? They're all from the bottom. It's not along the edges. There are not enough edges, to have all the pins. So they're all coming out from the bottom, okay, in order to give you, 2,000 connection points. Now, if you just look at what is the square root of 2,000? Just to look at the size of these problems. 40 something, 50 something? 44? Okay, close enough. So if you're looking at the square, this is your chip. It has got 44 columns and 44 rows, 44 columns. And when you draw, the interconnection between these, every single connection is a pin. 44 by 44. And how big physically is a chip? It's not that big. Okay, modern chips are not that big anymore. Back in the good old days, there are chips that are about the same size as a kitchen tile, a small kitchen tile. They're not that big anymore. So we're looking at very high density of pin count. And how do you make sure that all 2,000 pins are making connections correctly? Because if one pin is not connecting electrically correctly, your chip is not going to work. That's why all the pins on the circuit board, on the motherboard, they're all spring-loaded. Each individual pin out of the 2,000 has a tiny little spring behind it to make sure that it is pushed up, with a certain amount of force to make sure that it has good contact to the bottom of a chip. Okay, if you have not put a computer together, you'll buy your own CPU, your motherboard, and you have to put everything together, you have to at least watch a YouTube video of somebody actually doing it. because, it's just fascinating, okay? There's certain things we just think, oh, that's simple, easy. How big is a heat sink? It depends, okay? It can be, some of the chips do not actually need a heat sink, like your cell phone. Where's the heat sink of your cell phone?
The body doesn't
The entire case, right? But the case is actually plastic in many cases, so it doesn't really do a very good job radiating the heat. But when you're talking about your i7 processor with how many cores these days? 8 cores? What is the power consumption of your 8-core processor? Is it 140 watts these days, thereabouts?
Depends on how many cores, like.
And it depends on how far you push it, right? If you overclock it, let's say 200 watts, right? 200 watts doesn't sound too bad. I mean, in the good old days, you see these halogen lamps, with 500 watts, right? How big of an area do these lamps have to radiate the heat? Lots. How big is your processor? Okay, your processor may be this big in terms of packaging, but when you look at the copper area, which is where the heat is actually taken away, what is the area of the copper? A lot smaller. So now you have to think about 200 watts being dissipated with a tiny little area like that. Okay, do you want to touch it with your finger?
No.
Exactly. So I'm just going a little bit overboard here because it's just fascinating. Okay, if you have not done something like that before, just watch a video of somebody doing it because it's just fascinating. How these components of the computers are actually manufactured. So I'll see you guys on next Tuesday, and I will give you a homework assignment based on the A-star algorithm. Just later.
Speaking of computers, there's my.
Oh, so you have a liquid cooled.
Because
So is the whole thing in a tank?
Well,
Or is it just a transparent case?
yeah. So.
Oh, it's a transparent.
That's the reservoir. It has a little pump. I overclocked the seat. It's an i5 4690K.
Uh-huh.
Overclocked it to 4.6 gigahertz. And I have the graphics card overclocked as well.
Is it stable at that speed?
Yeah.
Wow.
It gets fairly hot. That's an older picture because I had to put 4 fans on my radiator because it was just getting a little warm.
You have to get one of those car radiators and attach it to your processor.
There was these guys, they took one of the new AMD Ryzen CPUs, the 1800X, and they overclocked it to like 6 gigahertz. But they had to cool it with like liquid nitrogen.
Well,
they had this like little
big
tank next to it,
yeah.
and it's like,
Wow.
That's crazy.
That is crazy. Because liquid nitrogen is actually not cheap. You have to. They won't even sell it unless they know that you know how to use it properly.
It was like a computer company that did the
Oh,
test,
okay.
and they were
Wow, that is crazy.
So it's like under class system, it also calls an LRC, and then it's the number of the classes. Like you should be able to redo it and figure it out easily.
Okay, because I was looking under.
Yeah, they changed it, but like all the documents allow you to check them. Like the documents